All right, good morning, everybody. Today we're going to take a look at the integral test, which is Theorem 9 in our book, if you happen to be following along to the book. The integral test is used when we want to determine the convergence or divergence of an infinite series, and we choose to use this when we look at the a sub n term of the series and we recognize that we could easily integrate that if it were a function. So that's what we want to take a look at. So let's look at the conditions and then we'll see how to apply this. So if this sequence of a sub n's are a sequence of positive terms, so these have to be positive values, and suppose that we have a function f of x where when we replace the x with an n, the integer values of the index n, we get the a sub n terms. So in other words, f of 1 is equal to a sub 1. F of 2 is equal to a sub 2, which are the various terms in this sequence. All right? And that function f is continuous, positive, and decreasing function for all x that are greater than or equal to some value of n. Now we saw this consideration before, and what this is telling us is that this doesn't have to work way over here at the left end for the function, as long as it works way out here at the right. So the first few values, or even the first dozen values, doesn't really matter so much. What matters here for using this test is what happens when we get way out there towards infinity. So as long as there's some point at which the function values match up with the sequence values of the a sub n terms, we're good to go. We do need to be able to identify what that number is and take that integral out in that territory. All right, so then once we've established that the function takes on the sequence values when n takes on integer values, and that it's continuous, positive, and decreasing, then we'll know that the series that sums the sequence of a sub n terms and the integral of the f of x both converge or both diverge. They behave the same way. Okay? So let me pick a function and we'll make a little graph and kind of get an idea of why this does that, and then we'll apply the test. All right, here we go. So let's suppose that we're interested in the series 1 over n squared. Okay, now clearly we could take a different approach than the integral test. I'm using the integral test with this because it'll be a quick example that we can all follow without too many details. All right, so now the function that we're interested in, f of x, is going to be a function that looks just like this a sub n term. That's going to be typically your strategy, is just convert that a sub n term to a function of x. And now you should be able to take f of n and let n go to the various integer values and get those same terms that you would get if you wrote out the terms of this series. Okay? So this is what we want to do, is we want to let this be our function, because then when we let x take on the values of n that we're interested in, the function values go to 1 over n squared, the values in the sequence of numbers that make this series. All right. Now graphically, let's take a quick look at graphically what's happening here. So if we just sketch up a little graph, if I let n equal 1, then f of, well, here, let's do this one first. If I let n equal 1, I get 1 over 1 squared, which is 1. That would give us a point right here. If I let n equals 2, I get 1 over 2 squared. That would be 1/4, roughly speaking right there. If I let n equal 3, I'll get 1 over 3 squared, about 1/9. So now we're getting down here. And so these points represent the values of the a sub n terms. Now if I graph this function, what I'm going to find is that this function, when x gets to these integer values, hits those points, but of course it's a function, so it's continuous, so it's going to also do this. It's going to come in from the left, and it's going to hit all those points. So what the integral test is doing basically is we're going to add up the area under this curve, say all of this from n equals 1 on out to infinity, and if that area is a finite area, then if we only add up some of the numbers under there, we don't add up the entire area but just a few values, it's going to have to also be a finite value, because it's going to be a smaller total than we're going to get when we add the whole area. That's the reason that this works. So what we're going to do is we're going to determine if this area is finite. If it is, then we'll know that the sum is finite. Okay? So let's apply the conditions of the integral test to this situation. So what we're really interested in is the function 1 over x squared. And remember from our definition, we had those three conditions we have to meet: continuous, positive, and decreasing. So we're going to test each one of those individually. Okay? So, is this continuous? And you should be able to articulate a reason why this is continuous. Now, 1 over x squared, that's a rational function, and rational functions are continuous everywhere except where the denominator is equal to 0. So yes, this is continuous if x squared is not equal to 0. And the only time x squared is equal to 0 is outside of the area that we're interested in. So in all this area we're interested in, it is continuous. So we're good on that one. You always got to check it though. Now, is it positive? That's our next thing that we have to check. Okay, and when we take a look at 1 over x squared, we see the numerator is positive. There's no sign in front, so we have a positive numerator. The value in the denominator, x, is being squared, and we know that any value that gets squared is positive. So we always have positive divided by positive, except when x is equal to 0. So, yes, if x is greater than 0, x squared is greater than 0, so it's positive for all x greater than 0. So yes, we passed that. So we've passed 2 of the 3 tests. The third test, is it decreasing? So how do we test for decreasing? We need to check the first derivative. So let's do that. Now, to take the first derivative, I'm going to write this function just a little differently. So I'm going to write f of x is equal to x to the negative 2 power. And you'll see, of course, the negative 2, and this is x to the negative 2 power. So we're good to go there. Let's go ahead and take the derivative. F prime of x then is going to be, and I'm always extra careful when I'm doing negative powers, so it's going to be negative 2x, and now I need negative 2 minus 1. I got to go to one lower power. Negative 2 minus 1, that's negative 3. And I think I'm going to write this way, negative 2 over x to the third. Remember, a negative power sends it to the denominator. The negative 2 stays up in the numerator. So, is this positive? I'm sorry. X cubed, is the denominator positive? Anytime you cube a positive number, a value greater than 0, because that's where we're interested in here, is positive values of x, you're going to get a positive value. The numerator is always negative, the denominator is always positive. So f prime of x is always negative, therefore we know, so f of x, the original function, is decreasing when x is greater than 0. And we're not concerned with what it does on the other side of the y-axis. We're not worried about this side over here, okay? Because we only need to show the integral out on this right-hand end. All right, so now we've showed that we are qualified. So let's go back to our definition. We've found a function that takes on the values of the sequence that form the series, and we found that this is continuous, positive, and decreasing. We checked that carefully right here, and so now we're ready to go ahead and apply the test. So once we found the function that has those three conditions, then we know the series of the a sub n terms and the integral from n to infinity of f of x dx both converge or both diverge. So if you meet these conditions with your function, then we know the series and the function are going to behave the same way. So now we just need to find out if the integral diverges or converges. So let's go ahead and take the integral. So what we're interested in is the integral from n. We're going to use 1 to infinity. We could use a value larger than 1 if we needed to, but 1 will work fine here. 1 over x squared dx. And much like before, I'm going to write it a little bit differently, but remember, because this is an improper integral, we need to take the limit as a goes towards infinity, and then we need to take the integral between 1 and a. And I'm going to write this again like I did earlier, x to the negative 2 dx. That makes this an easy integral to solve. So let's take our limit as a goes towards infinity. And now when we integrate x to some power, we go to one higher power and we put it over that higher power. So x to the negative 2 is going to go to x to the negative 1 over negative 1. And I think I'm going to rearrange this a little bit before I do my evaluation. So let's get all our notation in play. There we go, nice and clean. We still need to take the limit after we do our cleanup work, get things rearranged so that we're happy. The negative 1, remember that with a fraction, a negative in the denominator can go in the front or in the numerator. They're all good there. And x to the negative 1 power is the same as an x in the denominator. We have to evaluate that from 1 to a. And then we're going to take the limit when we get that all done. So now we need the limit as a goes to infinity. And now we're going to evaluate, and it's upper minus lower. So this is going to be negative 1 over x gets replaced with a minus negative 1 over x gets replaced with 1. Upper minus lower. So I'm going to clean this up one last time, and we should be ready for a limit. Negative 1 over a minus times minus plus 1 divided by 1, 1. All right, so this integral then, when we let a go out to infinity, the denominator of this fraction gets large, and we know that when the denominator of a fraction gets large, the value of the fraction gets small, and so this is going to go towards 0. As a gets out closer to infinity, the value of the fraction is going to get closer and closer to 0. Of course, the 1 doesn't change in value as a goes towards infinity. There's no a's here. So this is going to be go towards 0 plus 1, 1. Now, the integral here has converged. So the integral from 1 to infinity 1 over x squared dx converges. So the series 1 over n squared converges by the integral test. And it's always a good idea, if you're doing a problem like this, when you get to the finish, to give your reason. So you state your conclusion. The integral converges, so the series converges, and give your reason by the integral test. It's a reminder, if you didn't say at the beginning, that you were using the integral test. So another option would be way up here at the start. You could say, let's try the integral test, right? And so it converges by the integral test is a great way to finish that off. Now, when do you want to try to use the integral test? Anytime you look at that a sub n term and you can think, geez, I could integrate that really easily, the integral test will be worth a try. All right? Thanks a lot.